Good evening, everyone, and welcome to the live session for the course NOC25-ae17 Elements of Mechanical Vibration. I hope I am audible and visible. If in any case there is an issue, you can tell me. Okay, so we are into the week 2 live session. I hope that you people have already gone through the online lectures for this week. And last week, we essentially discussed about single degree of freedom without any damping, right? So we were mostly concerned about finding the equation of motion and the ways in which we can find the equation of motion, and then how we can find the natural frequency of the system. And we did some questions for different kind of system, that how do we actually find the natural frequency, right? And we also discussed about that for a continuous system we can actually model it as a single degree of freedom system, like we discussed about the case of a beam, cantilever beam. We actually modeled it as a single degree of freedom system, spring mass system. And then depending upon what is the equation for a cantilever beam, if we apply a load at the end of the cantilever beam, then depending upon what is the displacement, using that equation, we related it with F is equals to Kx, and then we found out the value of K, and then putting it into the material parameters like the flexure rigidity, the area, and the area moment of inertia. We use that to find out the effective stiffness, and then we use that model to find out that what is going to be the natural frequency of the system, right? And I hope it was clear to all of you. Now in this week's lectures, the introduction of was made for the damped vibrations, for the damped single degree of freedom system, right? Last week we were discussing about something like this. This week we have dashpot over here with a stiffness, and then we have a mass. Right? Now we have introduced the damping into the system. Now, what was the need of adding damping? Well, it's known to us that in a physical system there is always dissipation of energy, and for that we added damping, right? So if you remember, for this system, if we gave any kind of a perturbation, it was having something like this vibration. For this system, it was having the vibration like this, okay, with respect to time. Now, there were different type of damping which was discussed. One was the viscous damping, and the second one was the structural damping, right? Because in structural damping, we actually found out the equation, which I think you must have gone through. So we'll just start by taking up the questions. So this question says that for a spring mass system, M is equals to 50 kg and K is equals to 5000 Newton per meter. Find the critical damping constant, damped natural frequency for damping constant, half of the critical damping, and the logarithmic decrement. Now, if you remember that for a damped system, we could have three kind of condition, right? One was over damped, under damped, and critically damped, right? So critically damped is the case when there is no vibration and the system settle down to the equilibrium point without any transient vibration, right? So depending upon what is the critical damping, we find out whether the system is underdamped, overdamped, or exactly critically damped. So for the question, we have mass M is equals to 50 kgs, K is equals to 5000 Newton per meter, right? We have to find the critical damping constant. So for this question only, I'll be doing a bit of a derivation just in order for you to revise. But after this, we'll be just using the equation of the critical damping. Okay. So if you remember, for this kind of a system, if you write the equation of motion, it is like mx double dot plus cx dot plus kx is equals to 0, which can be further rewritten as x double dot plus c by m x dot plus k by m x is equals to 0. Okay. Now, if I want to find out the roots of this, or to be precise, if I want to find out the solution. So if you remember that for a differential equation, ordinary differential equation of this form, if we want to find out what is the solution, so we find out the roots corresponding to this differential equation, and then we can write the solution in, like, for example, this we can write as t square plus c by m d plus k by m into x is equals to 0, right? So for this, if I find out the roots, I assume that there is some lag. Okay, now it's fine. So for this, if I want to find the root, I'll get as s1 comma 2. Since it's a second order system, I'll get it as c by 2m plus minus under root of, this should be 4. Yes. So now if I have these roots, I can write the solution of x in terms of time t as a e to the power s1t plus b e to the power s2t, right? This is what comes from the concept of ordinary differential equations. Okay, so this is what we get as roots. Okay, now when we analyze this, we get that the term that is inside the under root, if it is positive or negative, it is going to decide whether my system is going to be underdamped or overdamped, right? When we say that it is critically damped, whatever is under the root should be equal to 0. Okay. Now, if we equate it to be equal to 0, okay, I'll just erase it. So I'm continuing over here, and I'll just write the answer as a e to the power s1t. Okay. So if I write c square by 4 m square is equals to k by m, what do I get? C square is equals to 4 m k. C is equals to twice of under root m k. And this is what is called as critical damping constant. Okay, this is the critical damping constant. Okay, so why is it called critical damping? Because at this value of C, what happens is that the root comes out to be real. Okay, and both the roots are same. Okay, if C is less than this, then what is going to happen? It is going to be a underdamped system. Okay, and if it is greater than this, then it turns out to be a overdamped system. Now, depending upon whether the system is underdamped or overdamped, the behavior of the system is going to change. Correct? Now, I've got the equation for the critical damping constant, right? Now, if I use it, anyways, if I use this in order to change the form of my equation of motion, what do I get? We have omega n is equals to under root of k by m, right? And then if we have this, we can replace it by what? We can replace it by to omega n, right? We want to not equal to, actually, we have to replace it by this. Okay. And you can do that also. How? See, if you have C by M and if you multiply it by this and divide it by this, you get C by CC as this, and then you have CC by M. Okay. So now, okay. So this can be written as what? Now, there is a question that why do we even need to change the main equation into this form, right? Because it helps us analyze whether my system is underdamped, overdamped, or critically damped. And on the basis of that, we know that how my system is going to perform, how its transient behavior is going to be, how it is going to converge to the equilibrium point, and everything of that sort. Okay? Now, as the question says, we have to find the critical damping constant first. Okay? So we know already that Cc is equals to twice of under root m k. 2 into, we have mass as 50 kg and k as 5,000. So 50 into 5,000. This is what we are going to get as a, this should be Newton second per meter. This is my critical damping constant. I hope this is clear. This is the answer for the first part. Coming on to the second part, which says that we have to find out the damped natural frequency for damping constant half of the critical damping. Okay, so we have the damping constant C as half of Cc. Okay, now we have to find out the damped natural frequency. What is the damped natural frequency? Now, if you remember from the solution that we wrote for spring mass dashboard system, in the power, there was something like e to the power omega n under root of 1 minus eta square into time. So that, because last time when we remember the solution for undamped system, it was something like e to the power omega nt. So if we relate that with the damped system, we get that the damped natural frequency omega d is nothing but omega n into 1 minus eta square. This was already done in the lecture also. Okay, so I'm not getting into how do we actually derive it. So this is the equation that we got. Now we have to find out the damped natural frequency. See, C is given as 0.5 of Cc. In that case, eta is what? C by Cc, which is nothing but 0.5. Okay, and then the question is, what is omega n? Sorry, omega n is nothing but under root of k by m, which is already given. K is 5,000 divided by mass, which is 50. So we get omega n as 10 radian per second. So in that case, the damped natural frequency is nothing but 10 into under root of 1 minus 0.5 square. This is 10 into under root of 1 minus 0.25 or 10 into under root of 0.75. Right? This turns out to be 8.66 radians per second. This is the second answer, which was about finding out the damped natural frequency. Okay. Now, the third part says that we have to find out the logarithmic decrement. Okay, so what was logarithmic decrement? So a derivation was done which taught us that for an underdamped system, we are going to have some sort of oscillations of decreasing amplitude, right? In that case, if you want to relate the amplitude of first cycle to the second cycle or the second cycle to the third cycle likewise, we define a term known as logarithmic decrement and we say that delta, which is the logarithmic decrement, is written as ln of xi divided by xi plus 1, and this is given as nothing but 2 pi eta divided by 1 minus eta square. Okay, where xi is amplitude at ith cycle and xi plus 1 is amplitude at I plus 1th cycle. Okay. See, in many places you must have seen that instead of using this particular equation, we generally, consider the denominator as 1, right? Now that is the case when our eta value is very small as compared to 1. Because you see, if eta is very small, its square is going to be smaller. And if we are subtracting that from 1, it is almost going to be 1 only. So for the sake of calculation, easier calculation, we neglect that. But in this case, if you see, eta is 0.5, which is a very significant value. Even if I square it, it is 0.25, which is 25% of 1, right? So here we should not consider the denominator as 1, but rather consider it. Okay? So considering that, we get logarithmic decrement delta as 2 pi into 0.5 divided by under root of 1 minus 0.5 square. This is 2 pi into 0.5 divided by under root of 0.75, and I've already done the calculation. It will turn out to be 3.6276. Okay, I hope it is clear. So the logarithmic decrement turns out to be this. Okay, I hope this is clear. This was a very easy question, right? Coming on to question number 2. We have, for a vibrating system, the parameter values are given as W as 10 Newton, where W is the weight. And it is evident from the unit also, Newton. K is 30 Newton per meter and C is 0.5 Newton second per meter. What are the logarithmic decrement and the ratio of any two successive amplitudes? Okay. See, as we studied earlier, delta is ln of xi by xi plus 1, which is nothing but 2 pi eta divided by under root of 1 minus eta square. But here we don't have the value of eta, but we have the value of m, k and c. So what do we have to do? We have to first evaluate the critical damping constant, and then on the basis of that we'll evaluate eta. So mass is equals to 10 by 9.81 because it is given in Newton. So we are dividing it by the gravitational acceleration, and this turns out to be 1.0194 kg. So I've done all the calculations already so that we can save the time for solving questions. So I should say that either with me only or after this session, you should do the calculations on your own. Okay. Then we have the stiffness as 30 Newton per meter, and then we have the damping constant as 0.5 Newton second per meter. Okay. Now, to evaluate eta, what do we have to do? We have to evaluate Cc, which is twice of under root mk. This will turn out to be 2 into m 1.0194 into 30. And this will come out as 11.4441 Newton second per meter. Okay. And then when we evaluate eta, it will be 0.5 divided by 11.4441. This will turn out to be around 0.0437. Okay, see, now this is very interesting. In the last question, we considered under root of 1 minus eta square, right? In this question, I can leave it because see, the value of eta is 0.0437. Even if I do a square of it, what will it turn out to be? It will be around 0.0018 something, right? So subtracting that from 1, it is not going to affect that much. Okay. So what we can do is we can for now consider it as 1. So delta is going to be 2I into 0.0437. This will turn out to be 0.2745. This is your value of logarithmic decrement. Now the question is that we have to find the ratio of any two successive amplitudes. So we remember that delta was nothing but ln of, okay, I've written it already, so we'll not be writing it again. From here, what do we get? We get xi by xi plus 1 is nothing but e to the power delta, which is e to the power 0.2745. This will turn out to be 1.3159. This is the ratio of the any two successive amplitudes. Okay, and this is applicable for all the cycles, right? It is nothing like it is nothing like that it is applicable only for some initial condition till we are actually we assume it in that way that till the vibration is not coming back to the equilibrium point, it is applicable. However, in physical condition it is not like that. Okay, in physical condition the non-linearity of the systems comes into play and then it is something very different, but here we are only concerned about the linear range of any of the system that we are studying. Okay, now coming on to question number 3. Derive the relation for the logarithmic decrement of system relating the amplitude x naught and the amplitude xn after n cycle have elapsed. See what this question is trying to say. So let us assume that we have a behavior something like this. Okay, something like this. So let us say that this is at time t1 and this is x. Okay, x naught and xn. I'll prefer it as x1 and this as xn plus 1 so that it will be easier to relate. So this will be x1 and then we have here at tn plus 1 as xn plus 1. Okay, this is the time axis and this is the x-axis. Now see, if you remember that we already know if this is a time t2, this is x2. We already know that the logarithmic decrement delta is going to be ln of xi or x1 by x2, right? But this time we want to know that how do we actually relate x1 and xn plus 1, which is the amplitude at t1 and the amplitude at tn plus 1 after the n cycles. Okay, so in that case what we can do is what we actually want is some delta n, which is, so we have essentially over here x1 by x2 is equals to e to the power delta. Okay, now what do we want is x1 by xn plus 1. This is what we require. How do we actually find it? So we can write it something like x1 by x2 into x2 by x3. I'm using dot over here because that cross is going to create confusion, into x3 by x4, likewise xn by xn plus 1. So what did we do? We had x1 by xn plus 1 and we multiplied it and divided it by x2, x3, x4, likewise till xn. Okay. Now if you see over here, x1 by x2 is e to the power delta. x2 by x3 is e to the power delta. This is also e to the power delta. As I said that this e to the power delta is applicable for all the ratios. Okay. Whether it is ratio of 1 is to 2, 2 is to 3, like xi by xi plus 1, I can be 1, 2, 3 till n plus 1. Okay. So by this, what do we get? We get x1 by xn plus 1 e to the power delta to the power n. And by the mathematical equation, we have e to the power n delta. Okay, so from here we can obtain now the new delta, which is nothing but, we should call it, yeah, logarithmic decrement only, is equals to 1 by n ln of x1 by xn plus 1. So now this equation gives us an advantage. You know what is the advantage? For example, we are trying to measure the amplitude. Okay, so we were able to measure at x1. Now we have to measure at x2, but we are not able to measure at x2 because let us say that the frequency is very high. Okay, so for us it is very difficult for any physical instrument where we have a limitation that okay, it can measure up to a certain level of frequency. Then what will we do in that case? We'll measure after some n cycle. Okay, like for example, whatever sensor I'm using, it has the limitation that it can measure up to, let us say, 20 hertz or 50 hertz. In that case, I'll not be able to measure at exact xt2. So whatever I have the minimum range of value that I can measure after a certain time, I'll measure the amplitude at that time. Okay, and then I can relate those two to find the logarithmic decrement. Only I have to do is that I have to divide it by the number of cycle that has elapsed. Okay, so this gives us an advantage that even if I have, it is not compulsory for me that I have to measure the two values of amplitude in one cycle only. Okay, what I can do is I can measure it after multiple number of cycles, and then I am just going to divide it by the number of cycles, and then I'm going to get the value of the logarithmic decrement. Okay, I hope this is clear. Okay. Question number 4. So question number 4 says that a body makes 5 complete oscillation per second. First thing that we are getting is that 5 complete oscillation in 1 second. Okay. So from this, what do I get? I get that it completes 1 divided by 5, which is going to be 0.2 second. Okay. And from this, what we can do is we can also evaluate the frequency. Now, in 50 cycle, its amplitude diminishes to 10%. Okay. Determine the logarithmic decrement and the damping ratio. What is the reduction percent of period of vibration if damping is removed? Okay. So the second information that we have is that in 50 cycle, its amplitude diminishes to 10%. So let us say at initial stage, amplitude is x1. After 50 cycle, x of 51. And we already have the relation that amplitude diminishes to 10%. So x51 is nothing but only 10% of x1. So x51, 51 is 10%, which is 0.1 of x1. Okay. So we have to determine the logarithmic decrement. Now, since we have this equation, it is easy for us to determine the logarithmic decrement, right? Because delta for a system where we have the amplitude for the starting and the end of 50 cycles, it can be written as 1 by 50 into ln of x1 by x51. 1 by 50 ln of x1 by 0.1 x1 ln of 10. After doing the calculation, you'll get this value as uh, okay, 0.0461. I've already done the calculation. You people can check it. Okay. Yeah, it was 0.0461. Yeah, fine. So this is the logarithmic decrement value. Now, the next part of the question says that I have to find out the damping ratio. Okay. Now, if you remember that we had the relation delta is equals to 2 pi eta by the root of 1 minus eta square, where eta was the damping ratio, right? Now, if you want to relate it, we get squaring on both sides. Delta square 1 plus eta square 4 pi square eta square. So we have delta square plus, we can just send it to the other side, 4 pi square minus delta square. Oh no, it should be minus. Yeah, to eta square. So we have eta as delta by 4 pi square plus delta square. Now you see over here, delta is very small. Now if I do a square of it, it will turn out to be a much smaller number. So there are two options. You can check also. First, where you should consider this and the second one where you consider it as 1. You're going to get almost the same value. For now, we'll just consider it. This turns out to be 0.00734. You see the value of eta is very small. So definitely we can consider 1 minus eta square as almost 1. Then also it will give us the correct value only. Okay. So this is what we get the value of eta. So we have found out the logarithmic decrement, damping ratio both. Now the next part of the question says that what is the reduction percent of period of vibration if damping is removed? Okay. For now, what is the period of vibration? 0.2 second that we have already calculated, right? We already know. What we have to do, we have to find out that what is going to be the period of vibration after we remove the damping. So for that, we know that omega d is omega n into 1 minus eta square. Omega d we already know. So we can use this to find out omega n, which is nothing but 0.2 divided by under root of 1 minus 0.00734 square. So if you'll find out, this will turn out to be 1.999 like this. Okay. So now if you want to find out the percentage change, it will be omega d minus omega n by omega d, and this you can calculate into 100%. It will come out to be a very small value. Okay, it will come out to be a very small value. Now we'll come to question number 5. So a bearing can be approximated at two flat plates. So this is basically related to the viscous damping part, right? So we discussed about that. Let's just leave it for now. We'll change it later. Okay. So as we know that for the viscous damping where we had F is equals to Cx dot. This was applicable for the viscous damping part, right? Where we were actually considering a fluid because of which if a force was applied, there was, parallel movement of the layers which caused some sort of dissipation, and that dissipation was the reason that there was resistance. Okay. So it is saying that a bearing can be approximated at two flat plates and offer a resistance of 4 Newton when a relative velocity of 10 meter per second exists between them. So what do we have to do? We have to consider two plates. Okay, we have two plates, something like this. Okay, so the question says that a relative velocity of 10 meter per second exists between them. So we assume that here the velocity is 0 and here the velocity profile is linear and it is 10 meter per second. Okay, and it is offering a resistance of 400 Newton. So if you remember that for viscous damping case we had F is equals to Cx dot, right? We have F, we have x dot. We can find C as nothing but 40 Newton second per meter. Okay. Now the question asks that the area of plate is 0.1 meter per second square. Then distance between plate is. So we actually have to find out the value of h. This is the area which is already known is 0.1 meter square. Okay. So if you remember that for this kind of system, for two parallel plates kind of system, we had shear stress as mu dV by dH. So if we consider the linear variation of velocity, we have shear stress as mu V by H. Okay. And this shear stress can be written as what? Shear stress is nothing but force into this area, this surface area A. So we have force by capital A equals to mu V by H. Mu A by H into V. This is what we get as C. This is what we get as C, which is nothing but damping constant. See, here we have already found out the value of damping constant. What do we have to do is we just have to find out the thickness. Now over here we know the area. We have to find out the thickness. We don't know mu. So usually in question mu is provided. I'll provide it over here. Consider it as 0.3445 Pascal second. Now if you put it in this equation, C is equals to mu A by H. Get H as mu A by C. 0.3445 into 0.1 divided by 0. This 40. This will give us the value of 0.86125 mm, millimeter. So this is the distance between the two plates. Okay. See, the thing that must be considered over here is that we had the relative velocity between them. It may happen that the lower plate must be moving with 10 meter per second and the upper plate must be moving with 20 meter per second. But we are only concerned about the relative velocity because the slipping of the layers are going to depend upon only the relative velocity and nothing else. Okay. So we can assume that the lower one is 0 and 10, 10, 20, whatever feels comfortable to us. Okay. Now, coming to question number 6. Okay, so we have a journal bearing is used to provide lateral support to a rotating shaft where R is the radius of the shaft, omega is the angular velocity of the shaft, D is the radial clearance between the shaft and bearing, mu is the viscosity of the lubricant, and L is the length of the bearing. Determine the total rotational damping constant. So as you remember, in the previous case, what were we doing? We were having actually a setup of two plates that were actually having a relative velocity between them, and a fluid was in between those two plates. And that fluid was actually causing resistance, because of which we were considering that there is damping present in the system. And using the, concept of shear stress and its formula, we actually derived the equation for the constant. Okay. Here we are going to do the same thing. The only difference is that here we are going to derive it for the rotational movement, right? We are going to derive the rotational damping constant. You know, like for example, if we have F is equals to Cx dot for a translational system, for a rotational system, we are going to have T is equals to let us say Ct into omega or theta dot. This is the analogy for a rotational system, correct? Now, we have a journal bearing, lateral support or rotating shaft. So let us first assume the shaft. So this is the shaft. We have the bearing, and then we have fluid filled over here. Okay, let us use some other color, maybe green. We have the fluid filled over here. Now, what do we have in the question? We have R is the radius of the shaft. This is R, radius of the shaft. Then we have omega is the angular velocity of the shaft. Omega is the angular velocity of the shaft. Okay. Then we have D is the radial clearance between the shaft and the bearing. So this is what we have as D. Mu is the viscosity of the lubricant and L is the length of the bearing. This is L. What do we have to do? We have to find Ct. Okay. So the first thing is that how is the velocity distribution? So if you see that the velocity is something like if I have this. This is my bearing and this is the shaft. This is some exaggerated view. Okay. And here we have fluid filled. Okay. So now if you imagine that how it is going to be with the velocity. So the fluid layer that is near to the bearing, it is going to have a zero velocity. Okay. And the fluid film which is near to the shaft, it is going to have a velocity of r omega. Correct? The linear velocity, omega r. Okay. So how's the variation of velocity? It is something like this. Here it is zero, here it is omega r. Should be capital R. Okay. I hope this is clear. Now, if I assume that, okay, if the variation is linear, then in that case, when we talk about the shear stress, which was dV by dr into mu. If the variation is linear, dV by dr is going to be nothing but omega r by d. Maybe I should not write it as r, I should write it as y. Any arbitrary distance, y. Okay, so we are going to have dV by dy. So this is essentially equal to r. So we will have mu omega r by d. This is clear. Now, if we talk about torque, what is torque? If I have the shear stress, I can multiply it with the area on which the shear stress is acting, and then I can find out what the torque. Okay. Now the question is, where are we going to have the shear stress? Where are we going to have the shear stress? See, there is fluid for all the thickness D. Okay. Now, what happens is that we are going to have a shear stress only at the layer of the shaft, but not at the layer of the bearing, because at the layer of the bearing is actually not moving, but the layer of shaft is. So it is going to experience a shear stress. So torque is going to be shear stress T into area. This is what? This is the force. And then we'll have to multiply the force with what? Arm length, which is R. This is going to give us the torque. Okay. So this is the torque that we have. Now we know that for this torque, this shear stress can be written as what? Shear stress can be written as mu omega R by D. Area is what? C. Area is going to be the circumference of the shaft. Okay, so area of the shaft is what? Area of the shaft is nothing but 2 pi r, circumference into the length, right? 2 pi r into length. This is going to be the area. So we can write it as 2 pi r L into the arm length. This turns out to be mu omega r cube L by D. There will also be a 2 pi. 2 pi mu omega r cube L by D. Okay, this is the torque. Now, if I relate this with this equation, what am I going to get? Nothing but Ct is nothing but P by omega. Okay, so Ct will turn out to be 2 pi mu r cube L by D. This will turn out to be our rotational damping constant. Okay, I hope this was clear. See, what did we do? In the earlier case, we were actually just using it, okay, by the relation that we got. It was also discussed in the class also. But for the rotational case, I took this example in order to understand that what if we get a rotational question. What we were doing in the previous week was that we were actually modeling our torsional or bending or axial system as a single degree of freedom system, which was fine. But if I give you that you model this torsional system as a single degree of freedom system, and if you use the equation of C as we obtained in the previous question, it will not be correct, right? It will not be correct for because for the movement theta we need to find out CT, and even if we want to relate it by just the relation like we use V is equals to omega R, we are not going to get the exact solution. But this is how it should be obtained for a rotational system. So now if you get a question that if you want to model a shaft for its angular movement, you have to use CT in this form and not in the previous question form. Okay, I hope that is clear. Now, coming on to question number 7. Now, this is a question where we will discuss about the structural damping. Okay. So, if you remember, we had the concept of structural damping because in that case, we were not actually having some kind of a viscous medium in our system, and the dissipation was happening because of the structure. So if you remember, there we assumed F, the force F, as Kx plus Cx dot, right? And then we said that C is equals to H by omega, and then this F was written as K plus IH x. Do you remember how we got this? So it was like x, x was something like x e to the power I omega t. So we obtained x dot as nothing but x omega I omega t. There was no t, I omega into x e to the power I omega t. So if we want to use this and write it over here, what are we going to get? We are going to get f as k x e to the power I omega t plus c I omega x e to the power I omega t. Okay, so this can be further written as x plus c I omega into, this was nothing but x. Okay, now if here I take common the value of k, then I can get it as k plus I beta into x. The beta was nothing but c omega by k. Okay, now, and if I write again c as h by omega, omega, omega will get cancelled. So there, from there we are going to get relation. Anyways, this was the final equation, and we wrote beta as the structural damping constant. Okay, we assumed beta as the structural damping constant. Now, there was a relation for the, like, same like that of a logarithmic decrement, that said that x of j by x of j plus 1, ln of this was equal to ln of 1 plus pi of beta. It was nearly equal to pi beta. Now see, this relation was is given in the book also. You can go to the refer to the book if you want to get into how are we going to get it. But this is the final equation that we are going to get. Okay. So now if we relate it, because if you remember for the case of logarithmic decrement that we were talking about with viscous damping, and if you want to relate it with that, what we can do is that we can assume that our pi beta is nothing but 2 pi eta equivalent. From this we are going to get that our eta equivalent is nothing but beta by 2, where beta was nothing but structural damping constant. Okay, so likewise we can get the value of eta equivalent. Okay, now for this question we have the values given as mass as this, then we have stiffness as Newton per meter, then we have the ratio of successive amplitude what is obtained as 1.04. Okay, so we have already the value of xi as xi plus 1, 1.04. This is given in the question. Okay, now if you see that if I have this relation, I can actually find out beta, right? The question is how. We have the relation this is equals to ln of 1 plus pi beta, right? If we remove ln on both sides, log on both sides, what are we going to get? x of I by x of I plus 1 is equals to 1 plus pi beta, which is nothing but 1.04. So we have pi beta as 0.04. From that we can get beta as 0.04 by pi. This will further give the value 0.10127. Now this is a very easy question if you know the relation. But how did we derive the equation is also very important. But if you just remember this equation that xi by xi plus 1 is equal to nothing but 1 plus pi beta, ln of 1 plus pi beta, you are going to get the answer. Okay, I hope this is clear. Now coming on to question number 8. So this here we have to find out the natural frequency of the system. The reason I have taken this question is that if you know how to find out the natural frequency for a system which is undamped, it is easier for us to deal with a damped system, right? For this circular system, what do we have? We have its moment of inertia Sj. We have its movement as theta. We have a mass m that is attached by a radius r1, and then we have a stiffness k. Okay. So what are we going to get over here? See, there are various ways of finding the equation of motion. One was the energy method, then there was force balance, there's method of virtual work, but we'll use the method of energy as of now. This is an undamped system, so it is going to have a total energy which is going to be constant throughout the time. The total energy would constitute kinetic energy plus potential energy. If I evaluate the kinetic energy, the kinetic energy is going to be there for because of two things. One is J, which is the moment of inertia of the pulley, and second one is due to M, the mass that is suspended. So we have half J theta dot square, then we have half M. Let us say it is X. The movement of X, M is X. Now how do we relate the movement X and theta? With a small circle, the radius R1. If there is a small movement theta, this is going to be X, and hence X is equal to R1 theta. So X dot is going to be R1 theta dot. So we get half J theta dot square plus half M R1 square theta dot square. Okay, I hope this is clear. This is the kinetic energy of the system. Now when we talk about the potential energy, which will be because of the spring only. Now for the upper circle, which has a radius R2, what do we have? There is a small movement like this, and this is theta. This movement is what? Nothing but R2 theta, right? For a very small value of theta. So potential energy is going to be half K R2 square theta square. Okay, we'll add. We're going to get the total energy as half J plus half M R1 square theta dot square plus half K R2 square theta square. Now since the total energy is constant throughout the time, if you differentiate it, it is going to be equal to 0. So d by dt of total energy is going to give us J plus mr1 square theta double dot plus K r2 square theta, this whole into theta dot is equals to 0. Now since theta dot will always not be equal to 0. So we get J plus M R1 square theta double dot plus K R2 square theta is equals to 0. So from this, using this equation, we get the natural frequency as K R2 square divided by J plus M R1 square under root. Okay, I hope this is clear. What did we do? We found out the total energy. Total energy was constant because there is no dissipation. So we differentiate the total energy with respect to time. And upon differentiating, we get the equation of motion. This is the we get the equation of motion, and from there we get the natural frequency. Okay, I hope this is clear. Okay, now coming on to question number 9. See, here is also a rotational system. The only difference is that in this rotational system, we have a dashpot. In the earlier question, there was no dashpot, right? But here we do have a dashpot. So there are two things that must be kept in mind. First, if we are deriving the equation, either we find out the forces and we balance it, right? Or what we can do is we can find out the total energy and differentiate it. But when we are finding out the total energy and then differentiating it, it is difficult, right? How it is difficult? Because there is a dashpot in the system which is actually taking up the energy, right? It is taking up the energy. So because of that, we cannot use the concept that we were using in the previous question, which was that the energy was constant. So we were differentiating the energy and making it equal to 0. Here it is not equal to 0 because the energy is reducing with respect to time, right? So the better way for doing this is that we try to find out the force balance method. Okay. Now, for the force balance method, we first need to know what are the forces that are acting. Now, there are two ways of deriving the equation. First, we consider x as our coordinate and then we find out theta, which is the movement of the pulley in terms of x. Or second, where we consider theta as the main coordinate and then we find out x in terms of theta. So here I'll consider theta only and then I'll write x in terms of theta. Okay. First, for this system, if I consider my mass is moving in this direction. Okay. My mass is moving in this direction, right? And then there is a this, which is going to have tension, something like this. Okay. But what is going to be the value of the tension, right? We can evaluate on the basis of what? On the basis of this mass and stiffness, right? So if the mass is moving in this direction, okay, I'm going to have the inertia in this direction. However, the spring is going to act in the opposite direction, right? But what is important is that if I consider that my P, which is the tension, is in this side, right? Left side. How is the force getting balanced, right? The mass is moving in this direction, which means that its acceleration is in this direction. However, the inertia of the body is going to be in the opposite direction, right? So essentially, what are we going to get? We are going to get P plus mx double dot plus kx is equals to nothing but 0, right? From this we get P, which is the tension, is minus of this. For now, we'll keep it like this. Now, the second thing. Let us now separate this. So what is essentially happening in this system? We have a pulley, then we have a small one. This is fixed. Here we have C. And here there is a tension P. Here there is a tension like this. Okay. Now, let us say that it is PC. What is going to be the value of PC? See, if PC is acting in this direction like this, we have, we can just not write it as PC. We know it is going to be equal to C theta dot into, this is R1 and this is R2. Okay. Now, if we try to balance the moment about this point, okay, if we try to balance the moment about this point, what are we going to get? For the pulley, okay, for the pulley, what are we going to get? For the pulley, we are going to get that J naught into theta double dot is going to be equal to what? It is going to be equal to CP is in the clockwise direction. So if we are considering the clockwise as positive, we are going to get P into R2 minus C R1 theta dot into R1. Okay, we are actually balancing the movement, nothing else. P is in the clockwise direction, it is creating a moment in the clockwise one. It is in the anti-clockwise direction, it is creating the moment in anti-clockwise direction. Right? I hope this is fine. Now, if we are going to write, right, if I put P over here, what am I going to get? J naught theta double dot plus M. Now see, X double dot, can I write it in terms of theta? Definitely I can. X is nothing but R2 into theta, right? So in that case, mx double dot is going to be what? M R2 theta double dot multiplied by R2, M R2 square into theta double dot plus C R1 square theta dot plus K R2 square theta is equals to 0, right? This is the final equation that we are getting. Okay, so this turns out to be J naught plus M R2 square theta double dot plus C R1 square theta dot plus K R2 square theta is equals to 0. Okay. Now, the question says that the amplitude of free vibration reduces by 80% in 10 cycles. Find the values of KNC. So basically, they want us to write it in terms of the logarithmic decrement, which we can do, right? Now, if I put the values of J theta, M, R2, R1, and K, what am I going to get? J naught 5 plus 10 into 0.25 square. C, they don't have the value. We have R1 as 0.1 square theta dot plus K 0.25 square theta is equals to 0. So now if I take up all the values, I get the final equation of the form 5.625 theta double dot plus 0.01 c theta dot plus 0.0625 k theta is equals to 0. This is the final equation. Now, for this equation, if I try to find out the logarithmic decrement, how am I going to do it? See, first things first. First, we'll try to find out omega n. What was omega n? If we relate it as m c k, right? And if I want to find out omega n, which is already given as 5 hertz, we get omega n is equals to 5 hertz. And we already know omega n under root of k by m. But this is in radian per second. So if we want to change it, we know that omega n radian per second is going to be 2 pi into hertz, right? So for radian per second, if I want to change into hertz, I'll have to divide it by 1 by 2 pi, right? So when I put the value 2 pi into 5 is equals to 0.0625 k by 5.625 under root, right? I can evaluate the value of omega n, sorry, k, which will be 4 pi square into 25 into 5.625 divided by 0.0625. This will give me the value of k, which will be Newton per meter. Similarly, I can find out the value of eta. How? See, we know that the center term, which is 0.01 c by 5.625, is going to be equal to 2 eta omega n. From here, we know the value of omega n, right? So if I put the value of omega n, okay, no, but for that we'll have to find the value of eta as well. Okay, sorry. This will come after. First thing is that ln of xi by x. How many cycles we are getting? In the question, we have the cycles as 10 cycle. So we are going to have I plus 10 is equal to 1 by 2 pi eta. So from this, we can get the value of eta. Now, since we know over here that the amplitude of free vibration reduces by 80%. So it was, if it was x1, it reduces to 0.2 of x1. If it reduces by 80%, so xi plus 10 is nothing but 0.2 of xi. So we have eta as 1 by 2 pi into 10 into ln of 5. This will give us the value of eta as 0.02566, right? And then if I want to find out the value of C, it is easy for me, right? Now even I don't even have to, either I can use this relation because I know the value of omega and I know the value of eta. I can use this equation, I'll get the value of C. Okay. I hope this is clear. I'll not get into the calculation so from here you'll get the values of C and K. Okay. Now, See, now we'll get into the questions wherein we'll have to find out the differential equation and the critical damping coefficient along with the damped natural frequency for our system. Firstly, what do? We find the equation of motion and then we use it to find the damped natural frequency and the critical damping coefficient. Now, if you remember for the system like this, mx double dot plus cx dot plus kx, we found out the root and on the basis of that we found out what were the critical damping coefficients and everything. So Cc was twice of under root of mk, omega n was under root k by m, and then omega d was 1 minus eta square into omega n, where eta was c by cc. Okay, we have to find the equation and then we have to relate it to this main equation. Then only we are going to get how we are going to find out the critical damping coefficient and damped natural frequency. Now for this system, we have a mass over here, which means that this is considered as massless. So it makes our computation easy. Okay, if it would have been having a mass, we need to have considered its moment of inertia as well. But for now, we don't have to consider it. Okay. So the moment of inertia for this mass is going to be what? ml square. And it is actually going up and down by a small value of theta. So this configuration is going to be something like this. Okay. And let us say that this small amount of extension is going to be what? For this angle as theta, we have this small extension as a theta. Okay, this is a theta. Now, if the spring is extending in the downward direction, definitely it is going to apply a force in the upward direction, right? So what we do, we have something like, at this point we have k into a theta, right? Similarly, for the case of damper also, the damper is getting compressed in the downward direction, so it is going to apply the force in the upward direction. Something like C A theta dot. Okay. Now, since we are considering the angular movement, we need to find out that how much of the moment it is applying at this point. We are considering it as a point where, like the point with respect to which we'll be calculating the moment. So we know that summation of all the moment about O naught is going to be what? It is going to be equal to I theta double dot. So we have I theta double dot is equals to force K A theta, right, into A. Now, since the force is acting in the downward direction, it is going to create a clockwise movement. Okay. Now, since we have considered I theta double dot as positive, it is going to be negative. Or we can consider this as, see, I hope that you people know that we have two equations. One is our Newton's method, Newton's first law that says that mass, summation of all the forces is equals to mass into acceleration, right? And then we have where we consider as the mass into acceleration as an inertial force. Okay, so we can consider it any of the both ways. So it is going to be minus, right? Here again we are going to have a minus for C A theta dot into A. Okay, I hope it is clear. Now this is what we are going to have. So we can write it as M L square theta double dot plus K A square theta plus C A square theta dot is equals to 0, which can be further rewritten as theta double dot plus C A by L square theta dot plus K A by L theta is equals to 0, right? Now, if you remember that how were we actually calculating the value of CC? It was like twice of under root mk, right? Now, if I try to find it out like that, how am I going to get it? See, over here, I have this as m effective and this as, sorry, k effective. So if I write CC, it is not going to give me the correct value. Okay, so this will actually not work in this case. Do you know why? See, because we have moments in this, okay? L square and A square. If we remove it, we keep the mass, but we just remove the L square part, right? We can get the correct one. How? I'll show you. Like if I use it like this here, should be a M and M. Okay? Now, instead of using this equation, if I use this equation, theta double dot M theta double dot plus C A by L square theta dot plus K A by L square theta is equals to 0. Okay. However, instead of using this, what if we use the main equation? We know how to solve it, right? What was the actual relation? It was like, for this I'll have two roots, which is going to be C by 2m A by L square plus minus under root of C A by L square by 2m square minus 4 will get cancelled because we have taken the 2 inside. It will give us as K A by L square by m. This is going to be inside the under root. Okay. Now we know that in order to find out CC, what do we have to do? We have to make whatever is inside the under root as equal to 0. Right? So now if we do it, C by 2m A by L square minus K by m A by L square is equals to 0. Whatever the value of C we are going to get from here is going to be CC, which is the critical damping coefficient. C by 2m right? Now If we cancel a by l over here, what do we get? We get c is equals to twice of m l by a under root of k by m, which turns out to be twice of l by a under root m into k. Okay, this is what we are getting. However, if we were using the m effective and k effective, we were not getting the same, right? Over here. So this is how we have to deal with it. We'll have to find out the equation of the roots, and then we have to put whatever is inside the under root is equal to 0, and from that we are going to get the value of cc. So cc we get out as 2l by a under root of mk. Okay, I hope this is clear. Now, coming on to finding out critical damping coefficient, we have already got equation of motion, we have already got, and we have to find out the damped natural frequency. So what do we have to find out for the damped natural frequency? If you remember, for the damped natural frequency, we had the relation something like omega d is equals to omega n 1 minus eta square, where eta was c by cc. Okay, so if you want to find out eta, what is it going to be? It is going to be, or rather finding this, what if we use the equation? We use the equation which says omega d is nothing but a by l under root of k by m minus c by a twice of ml square, right? What do we get from here? We get that a by l into under root of k by m into 1 minus c a by, we have taken k by m as common, okay? So if you have taken k by m as a common, it will come inside as under root of k by m, right? And the m is going to get cancelled. So it will come out to be twice of L under root K M. So this will be nothing but omega n to 1 minus eta square, where omega n is C A by L under root K by M omega n, and then we have eta, which is equal to C by Cc, as nothing but Ca by twice of L under root of K by M. Okay, I hope this is clear. Now, coming on to question number 11, which is somewhat related to the same type of problem. Now look over here. There we were having a mass, and then there was somewhere in the between of it, we had a spring and dashpot, which were at the exact same position. But here the mass is at a distance a from the fixed point, and then we have, after a distance of b minus a, the spring k. Okay, so over here if we find out, we have the mass, then we have a spring over here. Both of them are at the same level actually. It is important to note. This is A, and this is nothing but B. Okay. Now, if this mass is going to perform the oscillations with theta, okay, what is going to happen? This is going to get converted here like this. This is going to be at the mass m. The dashpot is going to be pushed downward and the spring like this. K, C. This is A, and this is B. Okay. And if this is theta, then how much is this distance? This is nothing but B into theta. And this distance is essentially A into theta. So the spring is going to apply a force in the upward direction as K B theta. And the dashpot is going to apply a force in the upward direction as C A theta. Again, if we are considering the movement in terms of theta, we need to find out what? We need to find out the moment of inertia, and then we need to find out the moments. So we have moment about O, which is this point, as nothing but I theta double dot, which is ma square into theta double dot. And this ma square theta double dot is going to be nothing but spring force K B theta into the arm length B with a minus. Then we have C, here it should be theta dot, A theta dot into the arm length A minus. Okay, so we have ma square theta double dot plus C A square theta dot plus K B square theta is equals to 0. Okay, so this is my equation of motion. Now, again, I have to find out the critical damping coefficient and the natural frequency. Now, if you look over here, you can write it as theta double dot plus C by M theta dot plus K by M B by A square theta is equals to 0. Now, this term is somewhat related to what we are having for a normal spring mass dashpot system, isn't it? Again, if we try to find out that what is going to be the damp natural frequency and everything, firstly, we'll find out omega n, which is nothing but under root of K by M into B by A. This is clear, right? Second, we need to find out Cc, which we can find out by using B square, which is nothing but C by M square by 2, right? There will be a 2 because there's going to be a 2 overhead, which we'll take out in the root. So it will be 4 minus 4 will get cancelled. K by M B by A whole square is equals to 0. So we have C by 2M is equals to under root of K by M into B by A. This implies CC is nothing but twice of B by A under root MK, right? This is what we are going to get. Now, what we can also do is we can try one more thing. We need to write CM, C by M as nothing but 2 eta omega n, right? Where eta is nothing but C by Cc, right? Now, If you want to write it in this way, how do we try it? We have 2 eta and omega n as b by a under root of k by m, right? So we can get eta as nothing but c by m into 1 by 2 b a under root of m k, right? Now if you look over here, if you look over here, you see that c by we have nothing but 2b by a under root of m k, which is nothing but what we got out as cc over here. So once you get the value of omega n, you can take out the value of cc like this also. Okay. And last we have to find out the critical damping coefficient and natural frequency. Yeah, they find out the natural frequency. We can also find out omega d, which is nothing but omega n into 1 minus eta square. And we have omega n as nothing but b by a under root of k by m. And then we have eta as nothing but c by cc, which is ac by twice of mb under root of m by k, which we can also write as, if we remove this, we can write it as b into under root of m k. So we can write omega d as nothing but b by a k by m into 1 minus a square c square by 4 b square m k to the power 1 by 2. This is nothing but the damped natural frequency. I hope this is clear. Now again we are going to take this question. This is going to be also an interesting question. So we have a uniform rod that has a mass m. This time the rod is having a mass m. In the previous question this was massless and we had only a mass, concentrated mass m at a distance a from the reference point. But in this case we have a uniform rod that has a mass. Okay. And then this distance is a, this is L. Okay. And then we have a spring and a dashpot. Now, if we consider that how it is going to deform, it is going to be something like, let us say, from the straight configuration, it is going to be something like this. So here, we have the dashpot, spring, and here we have the dashpot, K, C. Again, if this is theta, what is this going to be? This is going to be A theta, and this is going to be nothing but L theta. So, what are the forces? Here, there will be one force. Okay, it will not be in this direction, but rather in this direction, right? Which will be nothing but equal to K A theta, and the one force over here, which is will be equal to C L theta, right? Now, Again, over here, we are going to have I, which is going to be moment of inertia of the rod. Now, since this rod is having a mass, okay, and it is having a mass m and a length L, its moment of inertia I is going to be m L square by 3, since it is pivoted from a point which exists at one end. If it would have been in the center, the moment of inertia would have been different. It is ml square by 3 because it is like a cantilever beam. Okay. Now we know I. So again, we know that if we take the moment about this point, which is O, moment about O is going to be summation. Summation of all the moments about O actually will be equal to I theta double dot. So we have I theta double dot is equals to, again, if you look over here, the rod is going like this, right? But the forces are acting in the upward direction. Okay. So what is it having? It is having that the moment is clockwise because of CL theta and KA theta. The moment is CL theta dot, sorry. The moment is in the clockwise direction. Okay. So it comes with a minus. So you have minus KA theta into A. Then we have minus CL theta dot into L. So what do we get? I theta double dot is equals to minus of K A square theta minus of C L square theta dot. Now if we put I is equals to ml square by 3, is going to be equal to 0. Now we can further change this equation in the form such that theta double dot plus 3c by m into theta dot plus k 3k by m a by l whole square into theta is equals to 0. Now from here we can again find out the natural frequency, the damped natural frequency, and the damping coefficient. How? Firstly, omega n is under root of 3k by m, and we can just keep the a by l out like this. This is going to be the natural frequency. Second one is finding cc. So we'll just do it both the ways quickly. Firstly, we'll write it something like 3c by m is equals to 2 eta into omega n. This implies 3c by m is equals to 2 eta into a by 3, sorry, a by l under root of 3k by m. This implies eta is equals to 3c by m into l by a to 2 under root of m. M is m by 3k. Now, if we further work on it, we are going to get 3c by 2a into L. into under root of 3mk, right? This is what we are getting. So, yeah, let me just check once again. We'll have eta as 3c by 2m, mm will get cancelled, L by A. Yeah. So from here, what we can see is that our CC is going to be 2A under root of 3mk by 3L, right? We can do it in that way also, where we do B square, which is 3c by 2m square is equals to nothing but this value, 3k by m A by L square, right? So we are going to get 3cc by 2m is equals to 3k by m under root A by L, which implies cc is nothing but 2a by 3l under root of 3mk, which comes out to be the same value as this. So both ways we can either use the discriminant or we can use this way. Okay. Third one is finding the damped natural frequency, for which we need omega n and eta. Omega n we already have, so we want eta, which is over here, this one. So we have eta as 3c by L divided by 2a into under root of 3mk. So we have the damped natural frequency as A by L the root 3 km into 1 minus 3 c square, okay, 9 c square L square by 4a into 3 mk to the power 1 by 2, which will turn out to be, I think, A by L the root 3 k by m into 1 minus 3 c square L square by 4 amk to the power 1 by 2. Okay, so this is going to be the damped natural frequency. I hope this is clear. Now I'll discuss briefly this question as well, although I hope that you people now will be able to solve this question. See, again, we have a mass which is connected to this reference by a spring and a dashpot. Then this mass is basically connected to a pulley, and that pulley is again connected to uh, the reference through a stiffness, sorry, not stiffness, it should be spring with a stiffness K2. Now, the question is now how do we find out the differential equation and the critical damping coefficient? Okay, so see, the first thing over here to notice is that it is somewhat related to what we have done earlier. The only difference over there is that here K2 is connected at a distance A from O. Okay, that is the only difference. Now, if I talk about the kinetic energy, what it is going to be, it is it will be because of M1, then it will be because of M2 and I2. First thing is relating theta with x, right? How would we relate theta with x? So if we consider that there is no slipping happening, in that case we can write x as nothing but r theta. right? We can write x as nothing but r theta. Okay. So if we now try to write the kinetic energy, total kinetic energy in terms of, let us say, theta, how do we write? So we have half m1 x square plus half m2 x square plus half I theta theta dot square. I want to change x in terms of theta. So I'll have half I naught plus m1 x is equals to r theta, right? Here should be dot. So x dot is equals to r theta dot, correct? So what do we get? We get that we can write x dot square as r square theta dot square. M1 r square plus m2 r square into theta dot square. Clear? This is the kinetic energy. Now let us talk about the potential energy. Now the potential energy of K1 is going to be because of the movement of x. We know that x is equals to r theta. So simply we are going to write it as half K1 r square theta square. Okay. Second thing is that what is going to be the movement of K2, right? Now see, when we are saying that the mass m is moving by x, and so this circle that we have of radius r, it is moving by x and it is also rotating, right? It is rotating by what? Theta, such that x is equals to r theta. Okay, such that x is equals to r theta, right? But now when we consider a, because K2 is connected to the from the center to the distance, it's like a, right? Now we know that x is equals to r theta, okay, which is fine also because theta belongs to something like this. From here to here, we have theta. Okay. Now, if we want to find out that what is going to be the displacement of K2, how are we going to find it? It's a big question, right? Because over here we have the distance as A. If we would have had the distance as nothing but like if it would have been connected at R, it would have been easier for us to find out the total energy, isn't it? But here that is not the case. So what do we do now? Right? What do we do now? See, if you remember, if you remember this question, now where's that question? Yeah, if you remember this question, we were also considering theta over here. The only difference was that this k was having a displacement is equals to x, right? This k was having a displacement is equals to x. And second thing was that its center was fixed. Its center was fixed. But in this case, if you look over here, the center is not fixed actually, but rather we are considering the displacement with respect to this point, right? We are considering the displacement with respect to this point. See, that is how we work with the no slipping condition. If the center would have been fixed, we would have rotated in terms of A. But here we are considering this point. The rotation is actually happening about this point, right? So how do we now write the displacement? Okay. So if you see clearly how it is happening. First, the center is moving by x. It is clear to us that the center of this pulley is moving by x. Second, apart from that, this K2 is moving because of the rotation. This K2 is moving because of the rotation happening with respect to the center. Now we know that this. If this is r and this is theta and this is a, we can write this as nothing but x by r into a, right? So the total displacement is coming to be x into 1 plus a by r. And then we know that x is nothing but r theta. So we'll have half k2 plus half k2 x square 1 plus a by r. So again, since we have a lack of time, we can just find the like differentiate, and we can get the total energy, and then we are going to differentiate it. But there's one thing that must be kept in mind in this equation is that there's a dissipation happening. So in that case, what do? We do it like T by dt of the total energy is equals to nothing but work done due to the damping. Okay, and from this we are going to get the equation of motion, for after which we can find the differential equation. Like the critical damping coefficient. Differential equation we can find like this only. Okay. So I hope that this is clear to every one of you. Okay. So this was it about today's live session. I hope that you people were able to understand. In case anyone has any doubt, we can discuss it in the next week live session. For now, this is it, and I hope this will help you in solving the assignment problems. Okay. So I'll end the meeting now. Thank you so much.